So welcome to Quantum Curious, and today I am going to review a paper, and the paper is from Nature Communication, and it is a very famous article in the field of device-independent quantum key distribution. And the title of the paper is Secure Device-Independent Quantum Key Distribution with Causally Independent Measurement Devices. And the author of this paper are Masanes, Pironio, and Antonio. So the abstract is quite amazing, and it describes that the device-independent quantum key distribution is a key distribution scheme like any other QKD scheme, and it depends upon the laws of physics and do not require any assumption on the internal working of the devices that we used for the key distribution purposes. So they say that the security of these kind of protocols uh, depends only on the correlations that violate a Bell inequality. So we know that there are certain quantum correlations that violate the inequality called Bell inequality, and this inequality was given by John Bell, and this inequality settled the debate between whether quantum mechanics is non-local or local. So quantum correlations are non-local correlations that cannot be described or explained by classical mechanics. So in this paper, they are using an independent devices or the measurement devices on which the key distribution scheme is based on. And they say that the secret key rate uh, of these of these protocols that uses these kind of devices is comparable to the standard schemes that we usually see in the QKD community, like PB84 protocol or the Gaussian modulated coherent state protocol that we saw in the previous video. So let's start with the introduction of the paper. So we know that the central problem of the cryptography is the distribution of secret keys, and it is impossible for classical cryptography unless we made some assumptions on the power of eavesdropper. So there is a shift of paradigm with the introduction of QKD. So we know that there is no assumption on the key when we talk about the QKD. But in classical cryptography, the security of the protocol depends upon the mathematical uh, hardness of the given key, like mathematical properties, because there are some assumptions that like uh, the factorization of some very large prime numbers. So if the Eve does not have that kind of power that it can solve these kind of mathematical problems very easily, so the security is guaranteed in that case. But QKD does not make any kind of these assumptions. So the security of the QKD protocol is solely based on the fundamental laws of quantum mechanics. So classical cryptography talks about that the key has no relation with the physical properties of the whole process, and it only depends upon and the security of the cryptography it only depends upon the mathematical properties of the given key. But in QKD, that is not the case. So the security is based upon the physical properties of the key generation process, like if we are using a BB84 protocol. So the security depends upon the polarization states and their properties. And if the Eve intercept the given polarization state passing through the quantum channel, and so the security directly depends upon the physical process that is generating the secret key. So device independent QKD protocols close the gap between the theoretical analysis and practical realizations of QKD. And it does not uh, require a characterization of the devices, as the devices can be corrupt or imperfect or even provided by the Eve itself. And in device-independent QKD, we do not make any assumption on the dimension of the Hilbert space of the quantum states that we are using. They can be continuous variable states or discrete variable states or any kind of states that we are using. So it does not depend upon which kind of state we are using in device-independent QKD protocol. So divide-independent QKD combines the advantage of both the classical and quantum cryptography uh, the security of the protocol depends solely on the key and the secret key that we intend to distribute between Alice and Bob or any two parties, and it also have the quantum advantage, the security also based on the quantum correlations, and they are guaranteed by the laws of quantum mechanics. So these kind of assumptions are made in this paper, and in this paper they are using the independent measurement devices that may be imperfect or corrupt, and they are making no assumption on these devices. So they in previous papers, these kind of correlations are also used for the security to prove the security of these kind of protocols, but they only use the no signaling condition or no signaling principle that states that the information cannot travel through space uh, more with the speed more than the speed of light. So in this paper, they are also making the no signaling condition, but also uh, uh, the correlations are quantum, like they cannot be explained with the classical classical mechanics. So let's start with the general structure of device-independent QKD protocol. So device-independent QKD protocols are usually the generalization of the protocols called Eckert QKD protocol. And this protocol is entanglement-based protocol. So the summary of this protocol is that we have Alice and Bob, and they are connected through a quantum channel, and they distribute the entangled states between them with the help of quantum channel, and they apply some kind of measurements based on some random input given to them. So the security of the protocol is based upon the equality that is given in equation 1. And this equality is evaluated on the basis of the you can say statistical properties of their measurement or statistical data of their measurement. And if the equality is violated, then they can be satisfied that there is a pure entanglement process between or there is a quantum correlation between their measurement, and they can be satisfied that their secret key is not intercepted by Eve, and it is totally safe to use these kind of keys for the encryption purposes. So one kind of Bell inequality that is more famous is called Clauser-Horn-Shimoni-Hall or CHSH inequality, and it is given in equation 2. So this kind of inequality is usually violated by the quantum states or by the measurement of the quantum states like the qubits, and it is solely used for the protocol-based protocols where we use like qubits. So if this kind of inequality is violated, then Alice and Bob are sure that the secret key is not intercepted by the Eve, and they can use it safely uh, for the encryption and decryption of the messages. So after uh, this step, the whole protocol is just like another QKD protocol where Alice sends the message about A, that A is the A is the measurement of the Alice, and Bob corrects his errors, and his measurements are B, and it changes to B prime when he uses the data uh, sent by Alice, and then they apply some kind of a universal random function on their given data to get final secret key that has no side information that could be stolen by Eve. So this is the general form of the device-independent QKD protocol, and it is uh, the uh, specific form of the ACATS protocol. That is the entanglement-based protocol, and its security only depends upon the balance inequality. That is the CHSH inequality that we had described in equation 2. So device-independent QKD model is just the generalization of the simple packets protocol, and there is no assumption on the state emitted by Alice, and uh, there is no assumption on the measurement devices that Alice and Bob are using. So consider we have X and Y, the inputs of Alice and Bob respectively, and they are using these inputs to decide which measurement have to perform on their quantum states that are entangled, supposed to be entangled with each other. So their measurement results are given by A and B, and the probability through which they get these measurement results based on their inputs is given by this probability distribution condition on their input X and Y. So we are considering that these are quantum systems, and these quantum systems are described by some state rho A, B, and the probability distribution should follow this kind of distribution in equation 3, and it is just the measurement. It is just the uh, measurement based on some commutator measurement operators, and they are applying on the given state rho AB, and the measurement outcomes are just the outcomes that uh, are that are that Alice and Bob are getting in the whole process, and these distribution are just quantum distribution given in equation 3. So there are some conditions on and assumptions on these operators that are describing the measurement on the given state rho AB. So these assumptions are very important in the device-independent QKD model. So the first condition is that their commutation relation is zero. In other words, if their commutation relations in zero, according to quantum mechanics, they are compatible observables, or their measurement results are independent of each other. And the equation 5 is another commutation relations, and it is saying that the measurement operators at different positions are compatible with each other, or it is saying that the consecutive measurements are independent of each other. So Alice and Bob uh, are doing many measurements, and these measurements should be uncorrelated or independent of each other. So this commutation relation is given in this condition is given described by this commutation relation in equation 5. So these two conditions are very important for the device-independent QKD model. So this detail is described in this. And another assumption is that the devices that Alice and Bob are using should be shielded, or they should be space-like separated. Or in other words, they should not transmit their measurement outcomes to Eve, so that Eve get can have some kind of advantage. So so the subsequent measurements should not be correlated with each other, and the devices that Alice and Bob are using in the protocol should be shielded, as they cannot transmit any kind of information outside the laboratories of Alice and Bob. So here comes the security proof, and we are trying to get a bound on secret key. So we have a 2n+1 system initially, and it is described by a tripartite state. And uh, after measurement of Alice, the classical quantum state is given by equation 7. And there is some correlation between the Alice's measurement, and the Eve system that is conditioned on the Alice's measurement. So the length of secret key depends upon the two quantities. The first one is the mean entropy, and the the number of and the data, or the number of bits that are used for the public communication between Alice and Bob, for in order to crack the crack the data. And it depends upon the uncertainty or the entropy of the Alice and Bob's data. So in order to crack these uncertainties, they have to share some kind of data with each other. And this is described by this quantity, that is npub. So mean entropy is the quantity that we are after with, and we are, for simplification, we are going to prove for the n is equal to 1 case, or in other words, for only one device, and we will generalize the given result after that. So the probability distribution of Alice and Bob's measurement results are given in equation 9. And if the probability of Alice given by some input is less than one, then there is some uncertainty uh, for the Alice's data, or Alice's data is not as much predictable. So to calculate the mean entropy, we have to calculate the maximum probability by which the Eve can guess the Alice's outcomes. So it is given by equation 10. And if this quantity is 1, then there is no unpredictability in the Alice's data, and Alice's data is much certain. So our wish is to have this kind of quantity less than 1, as we want that Alice's data is quite uncertain from the point of view of Eve. So we want to have a bound on this quantity, and the bound on this quantity is quite related to the Bell's inequality. So the expected Bell inequality is given as this, and it is directly related to the probability distribution that Alice and Bob are getting in form of their outcomes. And it could be written in quantum mechanics in the form of some kind of inner product between between the given density matrix and an operator, and this operator is the Bell operator given in equation 11. So here A and B are measurement operators that are depending upon the inputs X and Y. So it has been seen that the guessing probability is bounded by some kind of Bell's inequality, and it has this kind of form. So our goal is to have these kind of inequality for different kind of Bell's inequality. So the general form that guessing probability is bounded by is given in equation 13, and where f is some kind of concave function and it is a monotonically decreasing function. So it could be formed in some kind of optimization problem, and we want to maximize uh, this quantity, and the constant we have is this. So given this constraint, we have to maximize this quantity as given in equation 14, and we have no assumption on the type of the measurement operator or the measurement or the uh, density matrix or quantum state that we are using. So it could be done by some kind of semi-definite programming or SDP. And in this paper, they are using some kind of hierarchy of SDP relaxations of problem 14. And they are saying that f is some kind of concave function and it is always monotonically decreasing. So this is a convex nature of the problem. So we uh, uh, get an upper bound of the f that is concave by some kind of linear relation or linearization of the function at point g naught. So we have to minimize this function as given in equation 16. So there is no assumption on the quantum state that we are using. So it gives us the equation 17. So these kind of operator inequalities are very helpful in bounding the mean entropy or the guessing probability of the Eve. So again, generalizing this result for n pairs of system, we have uh, Eve and she has system epsilon, and she is performing some kind of measurement on her system and getting some result like this. And the guessing probability of Eve is given in equation 18, and it is maximized over some probability distribution depending upon some measurement. So we have n operators given in this kind of form, and the probability distribution of L's outcome depending on the Eve measurement is given in equation 19. So uh, this is a general form of the result, and where rho AB is conditioned on the Eve's measurement and its out and her outcome. So the generalized form of the Bell operator is given in equation 20. So as given above, the uh, measurement operator is bounded by the Bell operator given in equation 20. And the overall problem summarized to this in equation 22. That is the minimum of the uh, trace of the given state and given Bell operator. So after doing some mathematical trickery and some kind of substitution of previous results, we get this form of secret key rate in equation 26. And it is upper bounded by the first term, that is the log of 2 of the given function that is depending upon the Bell inequality, and the uncertainty between Alice and Bob measurement results. So the main result, that is the main advantage of the whole process, is the first term of the secret key rate. So this bound on the secret key rate constitute the main result of their work. And this gives us the secret key rate bound for any kind of Bell inequality, whether it is such CHSH inequality or any kind of inequality for a higher number of dimensional states. So after that, they are representing some kind of key rate comparison for some kind of chain inequalities, where they are using 2 inputs and 3 inputs, and they are showing the effects of the noise on the secret key rate. So for less outcomes, for less inputs, like for CH in the case of CHSH inequality, the effect of noise is quite pronounced, and in the presence of noise and using the CHSH inequality, they get very lower key rate. But on the other hand, using uh, many outputs, like 3 outputs in that case, and the secret key rate is much larger, even in the presence of noise. So this is the advantage of using more generalized Bell's inequality. And this is given in equation like in figure 2. And they're describing that the key rate is much higher for the chain inequality using more inputs, like 3 inputs in that case. And the discussion they are doing is worth discussing. So they compute a bound on the key rate for a large class of device-independent QKD protocol, and their approach is quite general, and it could be applied to any Bell inequality, whether it is CHSH inequality or any higher dimensional inequality for high dimensional states. And uh, uh, the general inequality gives us more better key rates, and it improves the resistance of device-independent QKD protocols to photon detection efficiencies. So they are discussing again the use of an independent measurement devices, as they should be shielded, and it is quite physically possible. And their results nevertheless show that the secure fully device independent QKD with key rates comparable to those of traditional QKD is in principle possible. But they are saying that their model is quite realistic, but in a sense is also some kind of limited, as they do not make any kind of condition on memory. So they are using the no memory condition in their paper, as the measurement devices should not use any kind of memory, as it could be detrimental to the security of the given protocol. So they are arguing that there's no assumptions on the measurement operators, as there's no assumption on the Hilbert space of the quantum state, and in QKD protocols or standard QKD protocols, there is no assumption on the devices. There is some assumption on the devices, but there is always the no memory condition in all the standard QKD protocols. So if they do not if they do not make any kind of assumptions here, that is totally fine, and it is not affecting the uh, security proof that they have done. So it is quite practical, and the device-independent QKD protocols could also be used for the key distribution purposes, uh, and they gave the comparable secret key rates uh, com as given by the standard QKD protocols. So overall, the security protocol, the security proof is quite fine, and they are saying that the device-independent QKD protocols using the independent measurement devices is quite feasible, and it could be used for practical purposes, and it has much higher uh, security than the standard QKD protocol, as we do not have any kind of assumption on the given state or any uh, assumption on the given measurement devices. So this is quite good and quite good for the future of the uh, uh, QKD protocols in principle and QKD technology in general. So this is for all, and I will see you in the next video. Thank you. Bye bye.